project scientist from the Johns Hopkins Applied Physics Laboratory. Harlan Spence, principal investigator from the University of New Hampshire. Greg Klutzing, principal investigator from the University of Iowa. And Lou Lanzarotti, principal investigator from the New Jersey Institute of Technology. And we'll begin first with Mona Kessel, our program scientist. Mona?
Thank you, George. So I want to start with answering a couple of simple questions. And if I could see my first graphic, please. I want to show a cutaway model of the radiation belts. Now, you've seen this before because this is our logo. It's been up on a lot of things. The two bright red areas are the radiation belts. You can see that they are encircling Earth, and if you can imagine them wrapping around, what they look like is a couple of donut-shaped regions. And these regions are full of very high energy particles, and they're in these regions because they're trapped by Earth's magnetic field. They exist from about 650 miles above the surface, and they go out, that's the inner belt, it goes out to about 8,000 miles, and then the outer belt starts about 12,000, goes out to about 25,000. Now that's in a normal situation, but when we get solar storms, and we've heard about some solar storms, when we get those, then the radiation belts can expand, in fact quite a bit. The inner belt can come down as close as 125 miles above the surface of the Earth. And that means that the International Space Station crosses through it, and other low-orbiting satellites. And the outer belt does the same thing. It expands outward, and that means that geosynchronous satellites that are there, and there are about 300 of them out there, those are also then encompassed by the radiation belts. So these belts provide some hazard to the assets that are out there. But now, having said that, I want to take you back in time, back to the 1950s, to the dawn of the space age, because the radiation belts were the very first discovery of the space age. And if I can get the next picture, please. Then I'm showing a picture of 4 of the pioneering scientists of the time, starting left to right: Carl McElwain, James Van Allen, George Ludwig, and Ernie Ray. So these 4 men were instrumental in a lot of the early science. And in particular, Van Allen, second from the left, he was lecturing widely around the country. He was trying to get people interested in science, doing science in space in particular, because he wanted to study cosmic rays. And the few sounding rocket missions that had gone before, they went up, they'd be above the atmosphere for a few seconds, and then they come back down. So a satellite would provide so much more information. And so he teamed up with George Ludwig to build the instrument, a simple Geiger counter, and with Pickering and von Braun, which if you see the next one, we can look at a picture of them. This is at the press conference after their successful launch. They put the rocket up. It launched in 1958, and it was a success and an important event around the whole world, international and national significance. So as soon as they got that data back, they started analyzing it. And at the same time, they're preparing Explorer 2 and Explorer 3 for launch. And those went up soon afterwards. But as they're looking at that data, it's perplexing because there are no counts in some regions. So why was that? It was confusing. We didn't know why. And so they go into the lab and they start to look at it. Carl McElwain in particular, he's in there. He's bombarding the counter with charged particles, and he finds that 25,000 counts per second, and he gets that many in there, then indeed the Geiger counter shows 0. So now there's a different question, because now it's a case of, okay, we have lots of counts. We have 1,000 times more than the cosmic rays that we had estimated that we have. So there were more rockets that went up. There were, in fact, in a period of 15 months, there were about 9 that went up. So Explorer 4 and Pioneer 3, they went further out, and they were able to see the outer belt. So they started analyzing the 4 that I showed you the picture of. They're analyzing the data, and they're trying to put it by latitude, longitude, and altitude, and they draw a map. And if you can see the next slide, you can see that. a picture on the left-hand side of the map they drew. And you can see that this is an early picture of the radiation belts. And Van Allen had deduced that there was trapped particle there. And this discovery of the magnetic trapped radiation got him on the cover of Time magazine. So later satellites, as you've heard a little bit of, CRESS and one called SAMPEX, which I want to show a picture, actually a movie of SAMPEX now, if we could show that, shows how dynamic the area was. We had no idea back in the 50s that it would be this dynamic. You can see the red regions again. They represent areas where there are lots of charged particles. You can see at lots of times that there are two distinct areas. These are the two belts. But sometimes the outer region almost goes away. And then sometimes it almost fills in the whole region. So what we have is a very, very dynamic situation. And with only the one satellite, either in the case of SAMPEX or in the case of CRESS, they couldn't figure out or unravel what was really going on up here, why sometimes it's extreme and sometimes it's not. That's a job for RBSP. So what we have here is a kind of weather, and we've talked about this before. It's something we call space weather. And if you show the next graphic, then you can see a picture of things that we've already mentioned before: single event upsets, charging, discharging. Solar panels can be degraded when on orbit. So we have these weather assets, or these satellites, that are really affected by what's happening in space weather. And we are very dependent on our assets in space, so this becomes more and more important. RBSP will address one area of this. It will look at what's going on with the satellites and assess the damage that's, well, not the damage to individual satellites, but the measurements that could cause that. So we are going to, with RBSP, both satellites will be broadcasting space weather data 24/7. Whenever they're not doing science data. And that data will be collected by ground stations in the US and also around the world. And if you could show my final graphic, this is a ground station that was built by the Korea Astronomy and Space Science Institute, specially to capture RBSP data. And so they're one of our partners. We have other partners around the world. And with these ground stations and their help, RBSP will be able to predict the extremes and the dynamic conditions of space weather. And with that, George.
Thank you, Mona. And now to Nikki Fox, the RBSP Deputy Project Scientist from the Applied Physics Laboratory.
Thank
Nikki?
you, George. So Mona's just done a really nice job of explaining where the radiation belts are and how we know that they are changing. The difficult thing for us to work out is why they're changing, why they change different times to seemingly similar drivers. We know that variations in the sun create strong geomagnetic storms here at Earth. But what we don't understand is how we really truly respond to them. The Earth responds to what's coming from the sun. So we say if the sun sneezes, the Earth catches a cold. And if we could run my first movie, please, what you can see here is kind of some of the symptoms of the cold. You're looking at the radiation belts and how they're responding to the sun. The red and green dots that you can see kind of zipping in and out there are actually representing the two spacecraft. And you can see them cutting first through the inner belt and then going out through the outer belt in a nice highly elliptical orbit. Here's the storm that's just hit. The trace at the top there is giving you an idea of when you see that big dip, the storm has arrived, and you can see that the radiation belts respond very, very strongly to the arrival of that storm. This movie is available on the RBSP and the NASA websites, and if you do watch it in its entirety, you'll see that the response to the two different storm events is actually quite different. Thank you. So sometimes we see the same events coming from the sun and the radiation belts pump up, they get much larger in size and much larger in energy. Other times they actually shrink and almost go away. And then there are times when the radiation belts seem to not know that anything has happened. So if we can go to the next slide, please. When it comes to radiation belts, we are not alone. All of the large magnetized planets in our solar system have radiation belt structures. So Jupiter, Saturn, Uranus, Neptune all have radiation regions very similar to what we see at Earth. And the processes that are causing these radiation belts are the same at the other planets as they are for us. If you look at the graphic, the bottom two panels represent the Earth and also the radiation regions at Jupiter. So we know fundamental particle acceleration is going on at each of these planets. It's also going on the same processes that cause acceleration in the solar wind, and also more than 6,000 light years away that are causing the Crab Nebula to glow in X-rays. It's all fundamental particle acceleration. So I always like to describe the mission as a fundamental science mission that has really strong practical applications. So we know what processes are going on in the radiation belts. We know it's almost like having making a cake. You know all the ingredients, but you're not quite sure of the proportions of each piece in each given storm. Sometimes one process is far more dominant than another, and that is obviously causing the radiation belts to respond differently to seemingly similar things coming from the sun. If we go back to the movie, please. So RBSP was designed to answer the questions of how these radiation belts are responding. We do that by really looking at three different areas. One, why the radiation belts are pumping up or increasing. One, why the particles are lost from them because they do return to their pre-storm states. And then how the ring current, which Harlan will be talking about more in a moment, how that is associated with the radiation belt changes and how one is affecting the other. So we have two spacecraft that are on orbit. The reason we need two is not just because it's better than one, but actually because they really are doing a job at looking at these different processes, trying to find out whether they're changing in time or whether they're changing in space. So if you imagine sitting on a life raft in the ocean and you suddenly go down and come up again, you don't know very much about what caused you to go down and come up. If you have a friend that is sitting on a life raft a little way away, you can say, well, did we both go down and up at the same time, in which it's a big scale feature like a tsunami? Did one of us go down and then the other one? How far apart did we see that feature? Did it grow? Did it shrink? And you can really start to look at the global dynamics of what's happening in the radiation belts. So that's why we have two. We do have them lapping so that sometimes they're very close together. They can be as close as 100 miles apart. And other times they're separated by a distance of about 3 Earth diameters, so about 23,000, 24,000 miles. So that's allowing one to be in the inner belt while the other is in the outer belt, so that you can do sort of cause and effect, see if the inner belt is responding to the changes in the outer belt also. The high elliptical orbit does allow us to cut through the heart of both the inner and the outer radiation belt. Why do you have to get up at 4:08 in the morning? It's not just because the weather is likely to be better at that time in Florida. It was actually chosen very specifically to allow us to get the highest possible science return from the mission. When we start the mission, we want the point that is furthest from the Earth, or the apogee, to be at local dawn. And then as the 2-year mission continues, that point actually walks all the way around, so it will go to every single local region. It will take us 2 years to do a full sweep of all of the radiation region, and the most important thing is it will allow us to do the dawn to the midnight sweep twice in that 2 years, and that is where certainly it's one of the most dynamic interests, scientific interest regions. That's where everyone's very interested in. So that will be sampled twice. The other big new capability that we have are just the wonderful science instruments that we fly. The spacecraft are identical, so we can do really good collaborating measurements between the two spacecraft. We have suites of instruments that measure the particles, the full spectrum of energies, right the way down from the cold dense plasma up to the very, very high energy protons in the inner belt, which we're very grateful to the National Reconnaissance Office for teaming with us and providing a detector that really is focusing on that inner belt, which has increased the science that we can do. We also have instruments that measure the magnetic and the electric fields around the Earth. So I'm pleased that I don't have to go into that anymore because we have our experts here. So George, that's enough from me.
All right, thank you, Nikki. Our next scientist is Harlan Spence, who was the principal investigator from the University of New Hampshire. Harlan?
Thank you, George. It's truly my delight to be here after working on this mission to its roots far back to actually the late 90s in my case. To be on the cusp of a launch is truly exciting. What's even more exciting is we are going after a long-standing set of mysteries in the radiation belt with instrumentation that will be fundamentally, I believe, transformational and allow us to answer old questions, but also to make new discoveries. If I could have the first slide, please. This is a model of the spacecraft, and if you could add the instruments now, I'd like to talk to you about the particle instruments that are on the RBSP spacecraft. There are 8 different instruments per spacecraft, and we need 8 because we're measuring across this huge energy range that Nikki mentioned, from particles that are very, very low energy. In our units, we talk about going down to 1 electron volt, very low energy, to particles that are moving near the speed of light at billions of electron volts. Huge energy range we have to cover. In addition, we're looking at different species. We're looking at protons, electrons, helium, and oxygen ions. So we have a suite of instruments and several suites of instruments. There are 8 individual instruments per spacecraft in 3 different investigations. The first investigation is called ECT, that stands for Energetic Particle Composition and Thermal Plasma. And there are 3 different flavors of ECT instruments that you can see there. One is called HOPE, one is called, and that stands for Helium, Oxygen, Protons, and Electrons. The second is called MAGICE, and that stands for Magnetic Electron Ion Spectrometer. And at the highest energy range, there's the last of the ECT instruments is called REPT. That stands for Relativistic Electron and Proton Telescope. Also on each spacecraft is an instrument called RBSP. That's the Radiation Belt Storm Probe's Ion Composition Experiment. And that instrument is looking at of the ions that create the ring current. The last instrument is the one that Nikki referred to from the NRO. That's called RPS, and that's the Relativistic Proton Spectrometer. I'll talk a little bit more about these later on in terms of what science they will accomplish. Next, I'd like to move on to talk about some of the challenges we have with these instruments. This is an incredibly harsh radiation environment, and we're trying to make these detailed measurements across the energy range and across the different species of particles that we need to answer the science questions. But we're doing that in the presence of this just penetrating radiation. So we have fantastic instruments that are designed to do that. One of the things we have to do, in addition to the energy and to the species, is to understand the directionality of the magnetic field. In a magnetic field geometry that's narrowing at different locations, they can bounce between these reflection points, and then lastly, they can drift across the field line. So we have gyration around, bounce along, and drift across. In the next slide, here's how those motions are realized in Earth's magnetic field. So now you can see the Earth, you can see a green colored magnetic field line through the radiation belt, and you can see this complicated trajectory in that one dimension. You can also see near the equator of the Earth the directions of how the different particle species drift across the magnetic field line. The next movie will bring this to life. It's kind of hard to see it in 2 dimensions, but if I could have this movie, which shows a particle now gyrating along this blue now magnetic field line, and as we pan back, you can see that it's traveling along a magnetic field line, and as it gets closer to the planet, those field lines are bunching together and it will reflect, it will bounce back, but in reality it's in 3 dimensions. We're now looking from the North Pole, and you can see that that particle is drifting around the Earth while it's doing this complicated motion. It's sort of like rubbing your stomach and patting your head. It's got all these motions going on at the same time. That was one particle, but now take trillions and trillions and trillions of them. They fill the radiation belt, all moving in these complicated directions. Part of our job is to make those measurements of the directionality. Why do we measure them? To me, a key element that we've heard before in terms of space weather is that killer electrons are space weather's villains. They are fantastic things to observe from the point of view of the physics. There's this cosmic accelerator literally above our heads that's taking particles and bringing them near to the speed of light. But they also can inflict damage that we've heard about. So one of the primary measurements we'll make with the RBSP mission are these relativistic electrons in the outer radiation belt that are at this very, very high energy. And we do that with the mag ice and the REPT instruments that I talked about. In the inner belt, we have trapped populations of the relativistic protons. And these have been very poorly explored in the past. And that's where the RPS instrument will be flourishing. I'd like to go to the next movie, if I would, and talk a little bit about what the lower energy plasma particles do. This is a movie from the IMAGE spacecraft of a region called the ring current. And here we're using a technique of remotely sensing that from a spacecraft far away. The region that you see illuminated is co-located with the radiation belt. And this region is bristling with electrical currents that disturb, inflate, and deflate the magnetic fields that control how these very energetic particles in the outer zone are operating. So we need not only to measure the high energy particles, but also the medium and low energy particles. That's the medium within which the radiation belts exist. Lastly, I'd like to show a movie that essentially is the baby pictures of our instruments. And if you could cue that roll. It shows the different instruments as they were coming to the spacecraft. Here's the mag ice instrument. They all have, you'll see, single apertures, and they go onto the spacecraft in specific locations, as that first visual showed. But I also told you that we need to be able to see particles as they arrive from all directions. This is where the spacecraft spin that you heard about is critically important. The spacecraft spin rate is roughly 5 RPM. So that means every 12 seconds, as these apertures that are fixed locations on the spacecraft spin around, we map out the sky and are able to build up this comprehensive picture of particle motion needed to answer the fundamental questions that become practical. So I would just conclude by saying that RBSP, in a sense, will be going right to the scene of the crime to watch the radiation belt particles in action, along with their accomplices. What is it that accelerates these particles? It's the electric and magnetic fields that exist and are co-located that determine their quote-unquote bad behavior. So many scientists have worked hard and long to get us to this point. We're very grateful for the teams that have built these particle instruments that are outstanding, and like never before in two locations, it will be fantastic. The science team stands ready. We're eager, anticipating, and very excited about the launch. Thank you, George.
Thank you, Harlan. Our next presentation will be from Craig Kletzing, the principal investigator from the University of Iowa. Craig.
So as Harlan has mentioned, we've all been working on this for quite a while now. We proposed, more than half a decade ago, and I need to say more than we are stoked to get this launched. What I want to talk to you about are the electric and magnetic field measurements that we're going to make on the spacecraft. There are two investigations. There's the electric field and waves investigation, or EFW. We always use acronyms. And then there's the electric and magnetic field instrument suite and integrated science, or emphasis. And those are the two sets of investigations that will look at the electric and magnetic fields. So if I take the spacecraft model here, I can show you the sensors that we use for the electric and magnetic fields. We have two sets of sensors on the ends of the booms. This is our search coil sensor. It looks like sort of 3 sticks at right angles to each other. We have the magnetometer sensor up here. Then you'll see here are some wire booms that come out. The spacecraft actually spins along this axis. Oops. And so these come out, and then we also have booms that go along the spacecraft spin axis as well. And there's a slide here which shows the labels of each of these various different sensors as they come out. And so all of these sensors go together to give us a clear picture of the electric and magnetic fields. Now you might say, why do we care about the electric and magnetic fields? Well, it turns out they're critical for the acceleration of the particles. That is what pumps up the radiation belts and makes them bigger and stronger. But they're also important for what causes the radiation belts to decrease. They can cause particles to get scattered so that they hit the atmosphere and are lost and never come back. And so by measuring these fields, we have the other half of the puzzle. We have the particles, as Harlan's described, and then we have the fields that cause them to change their behavior. Now, we measure over a wide range. There's a lot of different kinds of phenomena that we want to measure with the field measurements, from very low frequency, very slowly varying things, up to things as high as hundreds of kilohertz. We need to measure across all these ranges, and that's what the instruments cover. Now, interestingly enough, many of the important waves that we're going to measure are actually in the audio range. They're the same range as human hearing. They're radio waves, but you can actually play them and listen to them, and they make a sound. And so we can listen to a little sound clip here. So this is the noise of space. This is a phenomena called chorus, and that's because if you'll notice, it sounds sort of like a chorus of birds early in the morning, you know, when they start chirping as the sun comes up. And that was actually why this phenomenon was named chorus. People measured this early on and said, oh, that kind of sounds like birds. And so this is one of the key wave modes that we're going to measure to try to understand what's going on. Now, as I said, there's a zoo of different waves. So we have a slide that sort of shows the various different waves here. And you can see there are all these different locations. I won't go into the details of what all these different waves are, but I think one of the cool things about the radiation belt storm probes is you'll see the two bigger dots there that label where the two spacecraft could be when they're separated along the orbit. And one of the things we fundamentally do not know is if one kind of wave is happening in one place, is the same or a different wave happening elsewhere? Does one lead the other or follow the other? Does one happen and the other doesn't happen at all? We don't know. So this will be the first time that we've got two spacecraft with the same instruments, so that we can actually start to figure out these kinds of questions. It's tremendously exciting to get this kind of data and put this together and understand something that we've just never seen before. Now, when you're making field measurements, you have to worry about making sure that what you're measuring is what's in space and not anything coming from the spacecraft. And that's why we put things out on these various different booms here. And so we have to check that that stuff works. And so we have a little video clip here of us checking the deployment of one of the emphasis sensors that comes out. And we do this in what we call a G-negated deploy. And that's where we do the appropriate things to simulate the fact that when the boom comes out, it's going to be in space and it won't be experiencing the effects of gravity. And that test went quite well, I should say. Of course, you know, doing it, you've got all this apparatus to put negate the effects of the Earth's gravity. So it's actually much more exciting, or much more elegant, I should say, to see this in space. And so we have an animation here that shows what that looks like when they deploy in space. And so you'll see one of the spacecraft sort of come up here, and first the solar panels come out. And then a little while later, you'll see the booms come out with the emphasis sensors on the end of them. I think this looks a little nicer than the test, but we do the test so that this happens the way you actually see it here. And so we're really looking forward to get that going. Now, when we do these things, we check everything out, make sure everything's working just fine. But we also want to make sure that the spacecraft doesn't produce a signature that we see on our various instruments. We say sometimes we want to hear the noise of space rather than the noise of the spacecraft. And so one of the tests that we do is we want to make sure that the magnetic field, I mean, anything that has metal in it's going to have some magnetic field, but we do our very best to minimize that. So we want to make sure that the magnetic field of the spacecraft doesn't show up in our sensors. But this is a tough problem because you're trying to measure, the requirement is that it has to have 1/10,000th of the Earth's field on the surface of the Earth is what you have to have to meet the requirements to be quiet enough. And so how do you do that? Well, what we do, and I'll show you this clip here, is what we call the swing test. What we do is we take the spacecraft and we hang it from a big cable. You don't see a spacecraft hanging from a string that often. You pull it back, but what we can see when we measure with the magnetometer is the part that's oscillating back and forth has to be due to the spacecraft. It can't come from anything else. And so that way we can verify that we have a nice clean spacecraft and that everything's doing what we want it to. And in fact, we do have a very clean spacecraft, probably one of the cleanest spacecraft flown. And finally, I'd like to talk a little about electric fields. Now, those are even more sensitive to spacecraft-induced effects. And so we want to get the electric field sensors as far away as we can from the spacecraft. So we let them out on wire booms that go out a long way. In fact, the tip to tip from one end of one probe to the other is longer than a football field. And those go out along what we call the spin plane. That's the plane in which the spacecraft is spinning. Now, you can't do that, though, along the spin axis because there's nothing to pull it out, no centripetal force. So there, a stacer boom is used, and they go out along the spin axis to get them as far away as you can. And there's a little clip here that shows the way the stacers pop, and then the booms extend out along the spin axis of the spacecraft, as you can see. And so with that, we get these measurements, we get them away from the spacecraft, we get nice quiet measurements, and that way we're measuring the noise of space rather than the noise of the spacecraft. So we're all very excited. We're here, you know, we've been working on this for a long time, and it's time to get this in space and get going.
Thank you, Craig. And our last presentation is from Lou Lanzarotti, the principal investigator from the New Jersey Institute of Technology.
Thank you very much. Well, the RBSP mission is back to the future for me. It provides an unprecedented opportunity to arrive at important new understandings of Earth's space environment. This was the exact motivation that attracted me to this field of research nearly 50 years ago. As the last mission of my career, I'm excited to be able to investigate Earth's radiation belts with state-of-the-art instrumentation flying within the belts themselves, seeking answers about the fundamental processes in Earth's space environment. Again, the same kind of questions that motivated me to join Bell Laboratories and the space program nearly 50 years ago, as I indicated. I began my career, first view graph there, I began my career at Bell Labs in 1965 to work on data analysis from the first active communication satellite, Telstar-1, and on the design and building of a radiation detector instrument for the first NASA test communication satellite at geosynchronous orbit, ATS-1, which we'll come back to. Second slide. Unfortunately, Telstar only operated for approximately 8 months in its low Earth orbit before it was seriously damaged by massive influxes of radiation, some natural from the Van Allen radiation belts and some man-made from atmospheric nuclear testing that occurred on the day prior to the launch of Telstar on July 9th, 1962. The Bell Labs team that designed and built and launched the Telstar satellite did not have a clear picture of the space environment above our planet at that time. Third slide. Before the launch of ATS-1, NASA's ATS-1 in 1966, which I participated in building an instrument for and analyzed extensively the data from, the radiation environment at geosynchronous altitude, where all of our modern communication satellites operate, was completely unknown. No measurements had been made there at that time. Next, fourth slide there. Bern Blake, who's a member of the RBSP ECT team, instrument team, was also a young physicist who had an instrument also on ATS-1. He and I are the two RBSP investigators who are from the very early days of exploration of Earth's space environment and that are back to the future, as I indicated. 50 years later, we understand much more about the hazards posed by highly charged particles in the radiation belt. But the fundamental processes that drive and shape the belts are still poorly understood, as we've heard several times today. Nearly 40 years ago, a colleague and I, Mike Schultz, wrote this textbook on radiation belts, particle diffusion in the radiation belts. This was the theory of radiation belts. It's been the theory to today. Data from RBSP is finally going to prove this textbook correct. I expect, however, we're going to find some surprises. And maybe we'll, if we have the energy, maybe we'll have to revise it. I don't know. We've been asked to revise it several times. We'll see. These mysteries of radiation belts, and as we described here 40 years ago, slightly less than 40 years ago, are the focus of our mission, as we've talked about. And I'm pleased to be able to be associated with it. Modern societies, and I've spent much of my career involved with applications of radiation belt research and communications and things. Modern societies dependent on satellites and other space-based technologies that must operate in the belts makes the research and understanding that will come from RBSP's data invaluable to building better protected satellites in the future for communications, for navigation, for remote sensing, and importantly for national security. Thank you very much.
Thank you, Lou. And we're ready now to take questions. Please give your name and affiliation when the microphone comes to you. We'll start with Marcia.
Marcia Dunn, Associated Press, with a few questions. I'm not sure who to direct this to. I previously asked, and I'll ask again, it's been more than 50 years since the Van Allen belts were discovered. Why take so long to get to this point? Is it because it's such a challenge, complicated? And if somebody could just sort of compare that original Explorer 1 with what's going to be flying in a couple days.
I can maybe speak to the particle aspect of it, and maybe colleagues can add to it. We have modern microelectronic technologies now that would have been the envy of the early explorers. The ability to pack highly sophisticated and capable instruments into a very small volume and small amount of mass allows us to do things even now better than when we first proposed the mission. So the advances even in the last 5 years have been highly enabling in terms of the kind of measurements. And a particular challenge, as I mentioned, with the particle instruments is being able to cleanly distinguish the particle that you're going after against the spurious signals you get from the penetrating radiation. And the sophistication of the instrumentation, again, is enabled by this advance in terms of the electronics.
Maybe I could comment on sort of why has it taken a while. And I think part of the answer is that we didn't know the radiation belts were as interesting as they've turned out to be for a long time. Initial measurements were made. Lou wrote the book, and okay, we think we have a pretty good idea, until some missions flew about 20 years ago, so 2 decades, and said, we looked at that data, and this is a little more complicated than we thought it was. But it takes a while to put together a mission, and those missions didn't have a very complete set of instruments. They had particle measurements and some limited field measurements, but not what you need to do the job correctly. And so people started working towards this, but it takes a while to put a mission like this together. And this is a phenomenal set of instruments. This is the best that's ever been flown in the radiation belts, and we'll make tremendous advances.
And in addition to that, we now have 2 satellites. That's a very important part of this, because with only one, you only know what's going on right there at that time, what's coming across. And as Nikki described already, when you have 2, and especially we're going to vary the separation distances all along the orbit and throughout the mission. And so we're going to get a feeling for, okay, we see it here, we don't see it right here, we see it here, we don't see it right here, but maybe we see something over here. So that whole picture will be built up by the variations in the separation distances, and of course whatever comes at us from the sun.
Yeah, and just to maybe add to that, because I thought somebody else would say this, but they didn't, so I'll say it. We actually now know the questions that we want to answer. So when when they were first discovered, as Craig said, we thought they were just 2 very stable bands of radiation. In 1991, the Air Force NASA CRESS spacecraft really started to show how dynamic they were with the discovery of a new belt when a big shock came through, and suddenly the gap that should be empty was now full. SAMPEX picked up, and then is actually still working today, although sadly will re-enter very soon. Was able to really track just how that dynamics has changed over 20, looking at 20 years. And also other missions that maybe aren't designed to look at radiation belts have returned really, really high quality data that, when you add to other data sources, have given us a lot of information and have really helped us over the 11 years since we did get together in September of 2001 to start doing the mission. It took a number of years to really hone the questions, get the right observations, choose the right instruments, and have the right technology in the right place to do the mission now.
You could, just a quick follow, is there anything on board or in the mission plan to honor Dr. Van Allen?
Well, we're not allowed to put things on the spacecraft that aren't fully blessed by NASA, so there's nothing on board.
James Dean with Florida Today. Ms. Kessel, perhaps, since you're talking about broadcasting 24/7, I just wondered if you might be able to make any kind of analogy to the modern media world in general, and kind of what these spacecraft will provide. It's sort of like a 24/7 cable channel or something compared to the Van Allen day.
Okay, so we will be broadcasting data 24/7. We will pick it up from ground stations around the world. Within about 12 minutes, that data will be out there available to the public. So just seeing the kind of data that first comes back, the very low-level products, that probably won't tell you that much, but we're also going to put that into models so that we will be able to show a picture in 3 dimensions that's going to be similar to what I was showing before of the dynamic changes. We're going to be able to put that kind of picture out there within minutes, but that's not going to happen on the day 1 that we launch, because we're actually assimilating that data into models, and so that product will be available fairly soon, I would think, but then on an ongoing basis it will be available every 12 minutes or so. So just like you see sometimes with SOHO, and I think SDO also, pictures of the sun, then this minute, the next minute, or 5 minute, however often the cadence is that they take the pictures, and it's out there available to the media. These products will be available. They will be out there.
Any further questions? Do you have a follow-up, James?
Yeah. Could you just address again, if there's a problem with one spacecraft, how much does that limit you? And I wasn't sure. I guess if I understand correctly, they're not communicating with each other, correct? They're just independently.
Yep, that's right.
Speaking to the ground.
They don't communicate with one another on orbit. All the data are downlinked, and then we do the collaboration between the two spacecraft, or the coordination between the data sets on the ground. If we are our mission success is to have both spacecraft operating for 1 year. If one does, sadly, something happens to it, then we can still do an awful lot with one spacecraft. The really fabulous thing about the mission is having two and being able to do these multi-point measurements. But as my colleagues have really stressed, the actual instrumentation on board these spacecraft is so high-tech and so cutting-edge that even with one, we're still stepping through all of the regions of the radiation belt, still cutting through all the most important regions, and still taking the best fidelity measurements we've taken yet, even with just one platform.
Although we do anticipate that they will both work. We have tested them extensively through lots of different conditions, and it is we do believe that we will have them both and that they will operate, and possibly even past 2 years.
I was going to say that, yes,
These are
maybe
a
even
couple of
past.
very
Yes.
tough birds.
Very, very armor-plated spacecraft, yeah.
On the line now we have Irene Klotz from Reuters. So Irene?
Hi, George. Thanks very much. I have a couple questions. The first is, and I'm not sure who'd be best to answer this, but I was wondering if there's going to be any collaborative studies with anything with the Cassini spacecraft or any other spacecraft that are looking at radiation belts and radiation environments around other planets in the solar system.
We don't have any collaborative efforts with that at the moment. However, we do with other missions. The Themis mission that's currently operating, we have members from both teams that come together, and we have discussed possible collaborations with them. And there's also a balloon mission that's part of LWS that was going to send 20 balloons up into space from Antarctica, and that will happen in January of next year, so 2013. And while those are up there, we will be able to measure precipitating electrons. So we will be able to see that while we're measuring in situ in the radiation belt. So we're really excited about that collaboration. So that one and the one with Themis, and probably also we'll do things with Cluster, which is primarily an ESA mission, but we have some U.S. participation. So we have been talking to other people, ground-based assets and various other things, but I don't think we have anything particular. Oh, okay, Nikki knows that we do. So
okay, we are actually going to have it's going to be very quick because it flies by very fast, but we are going to have a coordinated campaign with Juno when that comes through the magnetosphere next year. They will be doing some cross calibrations with their instruments, looking at the radiation they measure in our magnetosphere and then the radiation that they measure at Jupiter. So that is, it's quick because, man, it's moving fast, but we will get two cuts as it comes past and through the Earth's magnetosphere. So.
Thanks, and maybe for Dr. Lanzarotti, hi. I wanted to know if why was it not suspected before the launch of Telstar that Earth would have something like radiation belts, since I believe it was known that the planet had a field already. If you could maybe explain a little bit about what causes the radiation belts and why its initial discovery came as a surprise. Thanks.
Irene, that's a long, long history, as you probably are aware to some extent. When John Pierce, actually, Arthur Clarke proposed a satellite in a certainly after the Second World War, at geosynchronous altitude. It was a science fiction kind of thing. But John Pierce at Bell Laboratories proposed the Echo reflection satellite, which was launched in 1960 with NASA. And then John Pierce in about 1954 had proposed an active telecommunications satellite, and that was before the discovery of the radiation belts. So I think it's quite fair to say, and it is fair to say, and knowing him a little, somewhat, we overlapped a little bit to labs, before he retired and went to Caltech. There was no expectation that the Earth's space environment was not anything but benign. Cosmic rays had been discovered about 50 years prior to the Van Allen radiation belts. Actually, 100-year anniversary of the discovery of cosmic rays is just this year. Dr. Hess over in Austria flew his balloons with him in them and discovered cosmic rays in July, August 1912. But other than cosmic rays, there was no reason to expect the Earth's space environment wasn't benign. And in fact, the physics text that I used in 1956, 1957, and I've shown this at other talks that I've given, showed the Earth's magnetic field with just nothing out there except for the stars and the sun. And I've shown that in the past to show what we really didn't know 50 years ago. And so then Van Allen's discovery of the Van Allen radiation belts did put the fact that there was radiation, and they did the best that they could. Telstar was built with just transistors, discrete transistors, soldered together. And as a matter of fact, our ATS-1 instruments were built with just discrete transistors soldered together with very limited memory. There were no ICs at integrated circuits at that time. They were all transistors put together to make your memory devices and all. And so one had very limited radiation. There was no radiation hardness of these transistors for Telstar. And in fact, AT&T flew some transistors that they used as radiation monitors in order to monitor the Van Allen belts at Telstar altitudes to get a better idea. But they didn't. But the expectation was the satellite would probably last longer than it actually did. But the data were so poor by that time, 1962, and during the design in 1961, 1962, that there was just no way to harden in the same sense that we use today that spacecraft. As a matter of fact, it was just the 50th, if I can advertise here for a moment and allow me to go on if I might for a moment. There was just the 50th anniversary of the launch of Telstar held last month at Bell Laboratories in New Jersey. Several of us were asked to give talks there. There's a video, a YouTube video talking about that event, which is quite interesting to look at. Walter Brown, at that time, who hired me at Bell Laboratories to do radiation belt research, as a matter of fact, gave a talk on his instruments, on his little transistors that he flew on Telstar to measure the radiation environment. And some of that data is still used today. And then I followed him talking about space weather and how it's important for communications to today. So Alcatel-Lucent, while no longer building spacecraft, is still involved and interested in this field of endeavor and research, as can be evidenced by the anniversaries that they held and people that they asked to come and give talks back from their prior staff. Did that help a little bit, Irene?
Yes, that does. But I also was wondering if there's, I know this is a huge question as well, but could somebody just give kind of a basic science explanation of why Earth and the other planets that have magnetic fields have radiation belts?
That's a very good question. I don't think we really understand very well. Mike Schultz and I talked about it a little bit in our book here, and my colleagues who've done a lot of theory also. We have all these very low energy particles in the solar wind that are coming out from the sun. Somehow these are energized, these are transported into the magnetosphere and to make the radiation belts, but it's really very poorly understood, and that's the whole prime purpose of this mission. I should point out, one thing I did forget was back in about 1954-55 time frame, which was when John Pierce was talking about Telstar and low Earth orbiting active communication satellites. There was a professor at the University of Maryland named F. Fred Singer. Fred Singer still is active in certain areas of research. Even today, he's close to 90 years old, I think, mid-80s anyway. And he did some calculations where he showed that if you put some particles into something like a magnetosphere, there was no such magnetosphere at the time, but into a dipole field like the Earth had, you could probably trap them. But his paper was sort of an obscure one in American Geophysical Union abstracts somewhere, and he never talked about how you could highly populate them, but he did talk about they could be trapping. And so there was some research at that time and speculation and discussion, but nothing intense. And we really still don't know how these low-energy particles in the solar wind get in the magnetosphere and accelerated and decelerated and how they populate. That's the whole point of this mission.
If I could maybe just add onto that, Lou, the thing that really is making it different for the planets that have them and the planets that don't have them is the strong magnetic field. So we know that it is the magnetic field at those planets that is trapping the radiation. Most of the radiation is already inside the magnetosphere. Our magnetosphere itself does a tremendous job of protecting us from the particles that are in the solar wind. So a lot of the particles are already living in the magnetosphere and get injected and trapped. And I think that really shows why Harlan and Craig both stressed how important it is not just to measure the particles, but also to measure those magnetic and electric fields, because without those, we wouldn't have the radiation regions that we see.
Can I follow on? Am I taking too much time?
So we've got time for one more question.
Okay, all right.
You can go ahead and make a brief point, and then we'll take one final question.
Well, on the point of waves, on the NASA satellite ATS-3, we flew a wave instrument to measure whistlers. It wasn't a very successful instrument at all, and it was looking back now, the history is that we just didn't know anything about the waves that could affect these particles at that time. It was very primitive understanding, which shows the importance of the kind of sophisticated instruments that we're able to do now, the comparison.
Okay, we'll come back here for one final question.
Hi, Christopher Hale from the Avion newspaper. I just wondered how the data from this mission will be used to protect future spacecraft or satellites that may be traveling through this region.
A number of different ways. The easy answer to that is to really do a far, far better job of modeling the environment in which they'll have to live and work. There are and it's two sides of the coin. You don't want to send something up that is not adequately shielded, and it either gets crippled by a space weather event, or its lifetime is dramatically decreased by, say, solar panel damage. The same token, you don't want to engineer something. You don't want to launch a battleship when a dinghy would have done. So you don't want to be it costs a lot more to launch, a lot more to build, a lot more to maintain. So you want to be able to engineer the design of the spacecraft so that you really are putting the right amount of shielding for the right region, and also to have a very good prediction of how long those spacecraft will last, because again, you don't want to, if you've got operational spacecraft.
The models that we currently have are about 30 years old. We can really use an upgrade to those models for future design and engineering purposes.
They're almost as old as Lou himself.
Thank you, Nikki.
In addition to the design models, we also have physics-based models that the RBSP data will really provide critically important information that's needed to deliver better predictive models. And as we build up extreme events, we'll understand the range of the kind of events that we need to shield against as well.
Right, a good chunk of the models now are sort of empirical models, and getting to this where you actually understand what's happening allows you to do better predictions. And of course the other aspect is our space weather broadcast, and the modelers are now thinking about how can I be pulling this data in that's coming down all the time so that we can at least do maybe only at this point an hour in the future, but that's still more preparation than we have right now.
All right, that will conclude our briefing. One programming note as far as launch coverage: the start time is unchanged for launch on Friday, August the 24th. Our NASA TV coverage will start at 1:30 a.m. Eastern Time for a launch at 4:07 a.m. And that will conclude our briefing today. Thank you very much.